So we're working on lipids right now. We saw an introduction to these fatty acids that are fairly nonpolar. The majority of the molecule is nonpolar. But we can do something cool with our fatty acids and we can turn them into soap. So that's the next piece that we're going to look at on the bottom of the page here. So when we talk about soap, you hopefully think about something that can dissolve in water, but also dissolve nonpolar things like grease and fats and things that you're trying to wash out of your dishes or your clothes. So to make a soap, we saw this back in chapter 13 as well, but we could take a fatty acid, like what I see up here, and I would add it to a really strong base, say sodium hydroxide. And when I add those together, then I would get as my major product this compound, and this is a soap compound. So look at it a bit here. I still have that carboxylic acid, but it's missing the H now. Also, something important has showed up that you might remember from chapter 13. I have charges now, and I still have this extremely long nonpolar tail. So sometimes you'll see soap molecules drawn with this little head. This is a polar head here. And then that long tail after it. And I also am going to add this bit of yellow because if you can remember, when I have those charges tell me that this is an ionic compound. So I'm just going to jot this down. Soap is an ionic compound, which a fatty acid by itself is not, right? So soap is an ionic compound because it has those charges. It's more water soluble, much more water soluble than just a straight up fatty acid. And we had seen that was really important in chapter 13 for changing some other water solubilities. And then finally, we can use a new word to describe our soap. And I would say that soap is amphipathic. Amphi being a prefix to say that it can do two things. So amphipathic, it can mix with water, and it can mix with lipids or other nonpolar substances. So this soap molecule is unique in that it has this nonpolar feature, and then it has these charges which make this head very polar. And this is actually going to be a negative charge here on that polar head. So how does soap work then? We have a couple of pictures for us. So if you take soap and you mix it with water, you're going to have at a particle level what we call micelles forming inside of that water. And what's going to happen is the micelles are these spheres. This one's kind of cut away, and these pink heads that you can see here in the soap molecule end up on the surface because those are near, these are little water molecules here. And then on the inside, this is extremely nonpolar, so I just wrote NP for very nonpolar. And so anything that likes water is on the surface, and anything that likes nonpolar areas is on the inside. So let me draw you an even simpler picture of this. So if I take just kind of a two-dimensional cutout of this, and I have my soap molecules, they arrange themselves in this sphere because like dissolves like, or like mixes with like. So I have all of my little COO heads, and don't forget they're all negative, so they all have a charge on them. And those fatty acid heads that also have charges on them are going to be attracted to water. So they're all negative, right? There's random just sodiums floating around in the water as well. But these negatives are going to be attracted to the hydrogens in water, right? So I get ion dipole attractions between the ions of soap and then the dipole in water. So this is my cutaway of my micelle. Now, what's so great about soap is it captures the grease and it carries it away in these little balls, right? So if I can think about in here, these are all nonpolar, right? And so you end up with these long grease molecules, long carbon chains. And what kind of attractions hold nonpolar to nonpolar? If you can think about attractions there, what's going to hold nonpolar to nonpolar? In here, I have London dispersion forces. So I have all these nonpolar things hanging out together. I'm going to have dispersion forces holding those nonpolars together. And then down here where I have the waters and the ions, I have ion dipole attractions. And so by adding base to a fat, and this could be an animal fat or a plant fat. If it's a plant fat, plant oil, you would call it vegan soap when you're done with it. But you take that fat, add it to base, you get this soap molecule with the polar head and the charge. Those assemble into micelles, and then the micelles are able to mix with water and simultaneously mix with the non-polar stuff on the inside. So that is a glimpse of how soap works. Next up, we will move to slide 2.